I'd like to do an explanation of a topic that in intermediate algebra gives a great deal of trouble, and that is functions, domain, and range. And in particular, this topic gives students in higher math a difficult time. So if you have trouble with functions, domain, and range, don't feel as if there's something wrong. I'm not understanding this. Most people don't understand it the first time. It takes a second look at it to really understand some of the concepts here. I hope to hold this explanation on a fairly elementary level, and hopefully by seeing the video, by going over it once or twice, maybe that will help give you an extra resource to understand this. Let me start with three function machines. And I'm using a handout that I wrote to explain functions, domain, and range. And I want to give you three machines. And I want to talk about these in just a minute in three different colors to help you keep them straight. I'm using a handout, and on page 1 of this handout on functions, domain, and range, page 2, the first function box says 3x plus 2. Right? The second one says 12 divided by x minus 3, and the third one says the square root of 4 minus x. I want you to notice about these function machines that I've drawn on the board, each of the machines has an input, each of them has an output, and each of them has a formula, doesn't it? Each of them has a formula. Now, what I'm going to do, I'm going to input a number into this first machine. Like, let's say I drop a 0 into this machine. The 0 takes the place of the x, and the machine calculates the value of this expression given that x is 0, and what number comes out the bottom. If you put 0 in place of the x and calculate, you get 3 times 0 plus 2, which would be 2. So what if I put a 1 in this machine? What would I get? 5. All right, out comes a 5. What if I put 10 in the machine? What would come out the bottom? 30 plus 2 would be 32. All right? Now tell me, the question I want to ask is, what numbers would be allowed to be put in this machine? You're allowed to put anything in that machine, aren't you? Okay? Now take the second machine, and what if I put in a 0 in the second machine? Put a 0 in place of the x, and what would you be calculating? 12 divided by negative 3, which would be negative 4, okay? What if I put in a 1? What would you get? 12 divided by negative 2, which is negative 6, okay? Does anybody feel impish? Like you'd like to give this machine something that it can't handle? What number would you put in that machine if you wanted to, let's say, stop the machine? Can you think of a number that you could put in this machine that would stop it cold? What? How about 3? What if you put in x equals 3? If you put 3 in this machine, then what would you get? 12 divided by 3 minus 3, which is 0. 12 divided by 0, you can't do it. Can your calculator do it? Your calculator can't do it. You can't do it. Could you do it last term in basic algebra, or whatever Algebra 1 course you might have had last year? No. Could you do it next year in college algebra or in calculus? Do you think maybe you'll learn enough math that someday you'll be able to divide by 0? No. Nobody can divide by 0, right? That's one of the major points of this section, is that you cannot divide by 0, right? Okay? Now, but x could be 4, couldn't it? X could be 4. 4 would give you 12 divided by 1, which would be 12. In other words, if you put a 4 in the machine, then you could get out a number like 12 over 1, which is 12. Okay? Right? Is there any other number that would not be allowed in the real numbers besides 3? I could put anything in this machine except 3, could I not? All right? Now, remember we're talking about real numbers. We're talking about real numbers, and we go to the third machine. Can I put in x equals 0 in this third machine? Can I put in a 0? What would you get if you put in a 0? The square root of 4 minus 0, the square root of 4, which is 2. Okay? Can I put in a 1? Now remember, we're talking about real numbers. If you put in a 1, you'd end up with the square root of 3, which is an irrational number. Now, it's not a rational number. It's not an integer. It's not a rational number, but it is a number. It's an irrational number, but it is a real number. You see, the real numbers consist of rationals and irrationals. Okay? So square root of 3 would be a legitimate number. Now, what if I put in a 4? Let's say x is 4, and I put in 4 in this machine, and I'd end up with the square root of 0. Can you take a square root of 0? Try it with your calculator and see. 0 in the machine, and then square root. Yeah, what's it come out? 0. Okay? I mean, all this we can do with calculators, right? Can your calculator do the square root of 3? Try it. Give your calculator a 3 and ask it to do square root. It gives you an answer, doesn't it? It doesn't give you the exact answer, but it does give you a rounded off version of that answer, whatever it is. What about division by 0? Can your calculator divide by 0? Try it and see. 12 divided by 0. What does it do? Error, undefined, it flashes at you. Your calculator cannot divide by 0. Over here, your calculator can do the square root of 0, can it? All right? Now, what would happen if I let x equal 5? What if I let x equal 5 in this expression? 5. Put 5 in place of the x, and then what would you get? The square root of -1, which in the real numbers, can you take the square root of -1? Give your calculator -1. Now, the way you might have to do that is give it 1 first, and then plus or minus to change it to a -1. Or if you have a graphics calculator, just give it the square root of -1, straight out. Whatever your calculator does. It won't do that, will it? What's it tell you? Error. Your calculator cannot do the square root of a negative number, can it? All right? So that would be no solution for this. In other words, of all these examples that I've given you 3 examples to show you the 3 things that are allowed or not allowed in the real numbers. First of all, division by 0 is not allowed. Division by 0 is not allowed in the real numbers. Secondly, if you have a radical involved, the radicand is that quantity in the radical. The radicand cannot be negative because you cannot take a square root of a negative number in the real numbers. Okay? And thirdly, if you have a problem such as the first one here, with no radicals and no denominators, then there are no restrictions, and anything you try to calculate with this would be perfectly legitimate. Okay? Are there any questions on that? Okay? Now, do you think in mathematics that we're going to be satisfied to be drawing function machines all the time? Can you see some mathematician going through a long mathematics problem drawing function machines for the students? No, I don't think so. In higher math, we're not going to be drawing things like this. This is a handy little gadget to help you understand the concept of what we're dealing with here. But in real life, the equations are, this is going to be given in the form of an equation, like y equals, oops, got the wrong color. Y equals 12 over x minus 3. Or this one, the green one down here, would be y equals 3x plus 2. The blue one would be y equals the square root of the square root of 4 minus x. Okay? So in other words, we're going to have an equation with two variables in it. Now, we've already introduced the idea of equations with two variables. That's what we're dealing with in the section previous to this section on domain and range. So, yeah, but sometimes instead of writing y equals, or y equals these, sometimes instead of writing y equals, we use a notation called functional notation. We'll write this: f parenthesis x equals to 3x plus 2. Or we might write, instead of y, we might write some other letter besides f. Especially if there's more than one equation involved in a particular setting, we might, instead of saying f, we could say what? G of x is equal to 12 over x minus 3. And after g and h comes, after f and g comes what? H. We could call this h of x is equal to the square root of 4 minus x. Just to give you some examples of the notation that we're using here. Now this f of x, we use f because it involves the word function. It's functional notation, which is a special notation that we use. And this might look like it says f times x. Do you think that says f times x? Might look like it. But this notation means f of x. F of x. This is read f of x. All right? And what it means is you pick a value of x. All right? You pick a value of x. Let me write this here. F of x. Okay? And if I were to say f parenthesis 0, this 0 is substituted in place of the x, right? By the way, we're back to page 1 of the handout. Flip back to page 1 of the handout and you'll see this happening. So we substitute 0 in place of the x, and what would you get? 3 times what? 0. Okay, and then plus 2. We substitute the 0 in place of the x, and you get 2. So the answer is 2. F of 0 is 2. Then the next thing I did, I said, what would be f of 1? So f of 1 means substitute 1 in place of the x. In this formula, substitute 1 in place of the x. Everywhere there's an x, put 1. And what would you have? 3 times 1, okay? 3 times 1, which would, and then plus 2, which would be 5. Okay? Any questions on that? Now, give me now, what would be g parenthesis of 0? Using the g formula now. See, here this was f. I said this one's f, and I'm saying this one is g. Now, how do we know that's g? Because I said it was g. I can make it anything I want it to be. See, I make up the problem. So you can use whatever letter you want, but if it says g of x is 12 over x minus 3, what do we do with g of 0? 0 minus 3. We do 12 over 0 minus 3, okay? 0 minus 3, which would be negative 4, okay? So the answer would be negative 4, okay? What if I asked for h of 0? In other words, h parenthesis 0. What does h parenthesis 0 mean to do? Put 0 in place of the x in the h formula. And that would be the square root of 4 minus 0, which would be square root of 4, which is 2. Okay? So the answer is 2. H of 0 is 2. So that's what we call functional notation. Any questions on that? Okay? Now, before I erase my function machines and go on to the next phase of this explanation, let me mention again, as I did at the beginning of this session, that there are 3 parts of every one of these machines. There's an input, there's an output, and there's a formula or a rule that assigns, if you take a value of x, it assigns a value of y. In other words, the input is the x values. We've got here, let me label this. We've got input, which is what? The x values. Input is the set of all, should I say, permissible x values. Okay? And then what comes out the bottom, if this says y equals 3x plus 2, and the input represents the x values, what do you think this output represents? The y values, okay? So the output represents the set of y values, okay? Let me see if I can clean this up a little bit then. So here's a typical function machine with an input and an output. And the input is the set of all permissible values of x. And we have an output, which is the set of all y values that result. And in the middle of this thing is a rule. Let's say it was 3x plus 2. And that 3x plus 2 is called the function. So what is a function? A function is like a rule that allows you to take x values and do a calculation on the x values and obtain the y values. It's like a formula, all right? So that's what we mean by a function. Now there's one more thing I neglected to mention about the function. And that is, to be a function, it has to have a special uniqueness value, property. It has to have a special uniqueness property. A uniqueness property says, if you notice that every time we picked a value of x, we put one value of x in the top, what do we get out the bottom? One value of y. One value of x in the top, one value of y out the bottom. That is a function. And if it doesn't have that uniqueness property, then it is not a function. So the thought comes to mind right now, is a good time to bring this up. Is it possible for something to not have that uniqueness property? Is it possible to have something that is not unique? Let me make up a new problem and try to keep it simple. What if I said that this function machine is the square root of x with a plus or minus in front of it? Plus or minus the square root of x. Now I want to know, is this a function? And when I say, is it a function, I mean, does it have this special uniqueness property? So if I drop in a 0, in other words, 0, one number in the top, will I get one number out the bottom? What would I get if I put in a 0? Plus or minus the square root of 0, which is 0, right? Now, what if I put in a 1? What would you have? Now, if I put in a 1, I'll end up with plus or minus the square root of 1, which is plus or minus 1. Do you see what's happened here? One value of x goes in the top, but you get two values out the bottom. That is not unique. Okay? Just because it came out unique once doesn't make it unique always. Unique means always unique. I'll never forget, when I was in English in high school, I wrote an essay and I said that something was very unique. And you know, they ripped me for that. Very unique. You know, there's no such thing as very unique. Uniqueness is not something that comes in degrees. There are not degrees of uniqueness. Either it's unique or it's not unique. So if something is unique, it has to always be unique. So if you can ever find a place where this is not unique, then guess what? It's not unique. There's no such thing as very unique. Either it's unique or it's not unique. And therefore, it's either a function or it's not a function. So if something has a plus or minus in it, what would that tell you about it, whether it's got a function or not? The fact that it's got the plus or minus in it tells you that when you drop a value of x in there, you're probably going to get two y values, right? And therefore, it does not have that uniqueness property. So to be a function, you have to have a rule and have that rule arranged so that you'll always end up with a unique value of x gives you a unique value of y. Okay? All right, now, I want to move on to the definition of the vocabulary that we use here. I've talked in very general terms without defining any new words for you. I've tried to keep it simple. Now let me give you two words. The input is really what we call domain. Input is domain. Domain. And output is really range. Output is the range. Input is the domain, and output is the range. I think maybe I need to clean this board off because it's getting kind of cluttered up there. All right? Now, on the handout, and by the way, if you're watching this by video and you'd like to get a copy of the handout, just call my office at 328 and let's see, what is my number? 328-2249. 328-2249, or at Hunt Club, I'm at 328-2345. You can call me at either of those numbers, and I'll be glad to get you a copy of this handout if you need one. All right, let's start with page 3 of this handout, and I'm talking about the idea of domain. All right? What is domain? Input. Set of all permissible x values. Set of all permissible. You know what? I think I misspelled permissible a few minutes ago. So I hope my English teacher isn't watching this. The one that got me for talking about very unique. All right? Or maybe I'm misspelling it now. Never mind. Instead of all permissible x values. Does it matter? All right. And what's the range? Range is the set of all outcome, and that would be y values. Okay? So we've got input and output. All right? Now, there are two things that are not allowed in the real numbers. Can you tell me what those two things are? Two things that are not allowed in the real numbers. Number one, you are never, never, never allowed to divide by what? Divide by 0. All right? Never divide by 0. In other words, what's the rule here? Denominators, let me write it this way. Denominators cannot equal 0. Okay? Second thing that's not allowed in the real numbers, and this is specifically to real numbers, what would that be? The second thing, you're never allowed, this has to do with radicals. What would you say about a radical? If there's something in a radical, what do you know about it in the real numbers? It cannot be negative. In other words, the radicand must be what? Greater than or equal to 0. Okay? The radicand must be greater than or equal to 0. Now let's go back to the first three problems that I already gave you. And I'm going to start with the middle problem of the three that I gave you in the function machines. Remember the first problem was, and let me see if I can remember what color these were. I think the first one was green, wasn't it? Y equals 3x plus 2. The second problem I gave you, I think I did in pink, was y equals 12 over x minus 3. And the third problem, I believe, was in blue, y equals the square root of 4 minus x. I want to find the domain of these three problems. Look at the first problem, y equals 3x plus 2. The domain means the set of all permissible x values. What values of x are permissible in this problem? Are there any restrictions? No restrictions, right? That means x could be what? Anything. From what to what? From 0 to infinity? From 0 to negative infinity? In other words, from negative infinity to positive infinity. Got the wrong color. The domain here would be, that's the wrong color. The domain is negative infinity to positive infinity, right? Okay? Now, what about the second one? The second problem, domain. Is anything allowed in this problem? There's something that's not allowed. In other words, let's see, what is required? What's not allowed in this problem? 3 is not allowed. In other words, whatever that denominator is, x minus 3, that's the denominator, right? And it is not equal to 0. Denominators are not allowed to equal 0, right? So what can you do with this? Rewrite it as x, add 3 to both sides. X cannot equal what? 3. In other words, all I did there, I just added 3 to both sides of the inequality. I said add 3 to both sides, and that would give you x cannot equal. For the domain, we might write this here. All real x not equal to 3. All values except 3. Okay, how about the third problem here? The third problem involves a radical. So what do we know about radicals? When there's a radical involved, then whatever is in the radical, that would be the what? 4 minus x. The 4 minus x would have to be, it can't be negative, can it? Because you can't have a square root of a negative, right? That's what we said. You can't have a square root of a negative. So if it's not negative, what does it have to be? Greater than or equal to 0. Okay? Now, can you solve that? We didn't do this a minute ago. We just kind of substituted some numbers in and kind of by trial and error we decided, well, certain values are not allowed here. But let's see, what would it be? If you wanted to subtract 4 from both sides, that'd be a good idea, wouldn't it? What would you have? Negative x is greater than or equal to negative 4. And then what? Divide by negative 1. What happens when you divide both sides of an inequality by negative 1? Change the sign, right? This all-important rule, this would now be x is less than or equal to 4. In other words, what's the domain of the third problem? X would have to be less than or equal to 4, which would be what? Negative infinity up to 4. Up to 4. And including the 4. Okay? Any questions on that? All right, now based upon these two things that are not allowed in math, or in real numbers, the two things that are required in real numbers is denominators cannot equal 0 and radicands must be greater than or equal to 0. I've come up with 4 separate categories of problems at the bottom of page 3. So the first thing I want to look for in a problem, let's say I take another problem that you've never seen before. Let me make up a problem that you haven't seen. I'm not going to make one up. I'm going to take one off the next page or two. And let's say that problem is number 8 on page 5. Number 8 on page 5. And it says, y equals the square root of 2x plus 5. And I'm asking for the domain. Find the domain. Now, first thing I look for, I say, is there a denominator in this problem? Is there a denominator in this problem? There's not, is there? So I don't have to worry about denominators. But what is there in this problem that I have to worry about? There's a square root, okay? So what I have to do to find out what values are allowed in this problem, to find out what values of x are allowed in this problem, I have to say there's a restriction here because it's in a radical. That restriction is 2x plus 5 must be what? Greater than or equal to 0, okay? And now I have to solve that. Now how do you solve that? Subtract 5 from both sides, okay? Subtract 5, and that would give you 2x is greater than or equal to, how much? Negative 5? And then what? Divide by 2. All right, let's divide by 2. Divide both sides by 2. That would give you x is greater than or equal to negative 5 halves, right? And what would that be in interval notation? What values of x, what interval are we talking about? Values of x that are greater than or equal to, that means to the right of, this number. So we start with what? Negative 5 halves. What kind of a symbol do we use on the bracket? Comma to infinity. And guess what, folks? That's the domain. That's the domain. Now I started to list 4 categories of problems. So if you'll flip back to page 3, one more time to page 3. If there in category 1, yes?
I have a question.
Okay.
If an x is greater than or equal to negative 5 halves, but you said up there it has to be greater or equal to 0 if you're dealing with a negative number below.
Okay. All right. He says, what if the x number is a negative number? Now, did we say that x can't be a negative number? Like we said that the quantity in the radical cannot be negative. So what if let's pick a number in here. Like this interval looks like it includes negative 2. Do you think negative 2 would be allowed in this? Negative 2. Take negative 2 because that's within this interval. Negative 2. And substitute negative 2 in place of the x. Do you think negative 2 would be permissible in this problem? 2 times negative 2 would be negative 4. Now, we're not allowed to have a negative in the radical, are we? Is that saying there's a negative in the radical? The fact that I said 2 times negative 2 is negative 4? Because you see, it's negative 4 plus 5, so the radicand is actually 1. So what's in the radical is really 1, positive 1. So the square root of 1 would be 1. So that's permissible. Okay? You see, I said that you're not allowed to have a negative. I think what I should have said is, I said you're not allowed to have a negative in the radical. You're allowed to have a negative in the radical if you've got some positives to overcome it. You're not allowed to have a negative radical. I think I said that wrong. I should say that to be more precise. You're not allowed to have a negative radical. Radicand. You're not allowed to have a negative radicand. Now, I finally said it right. Okay? All right. Now, back on page 3, at the bottom of the page, there are 4 categories of problems. The first category is if there is a denominator. What's the stipulation if there's a denominator? The denominator cannot equal 0. So if we've got a category 1 problem, category 1 is denominator, and the requirement is denominator cannot equal 0. That's category 1. If there's no denominator, what do we look for? Category 2. So category 2 is going to be where there is a radical. And guess what? If there's a radical in the problem, what are we going to have for a requirement? The radicand must be what? Greater than or equal to 0. You see that? That's the second category. Category 3 is a new one. I haven't mentioned this category 3 before, but here we go. Category 3, what if there's a denominator radical? denominator and radical. In other words, there's a denominator radical or a radical denominator. Like maybe what if it was y equals 1 over the square root of x minus 5. Something like this. Now you see you've got both a denominator and a radical, so what's the requirement? If it's in a denominator, what is it? It can't equal 0. And if it's in a radical, it can't be negative, right? So what's left? If it can't be 0 and it can't be negative, what do we know about this? What do we know about this x minus 5? It has to be greater than 0. Okay? See, it's like a combination of both of these categories. Right? The first thing here, what I'm saying here is, if you have a denominator and a radical, all right, then the radicand, because it's in a denominator, cannot equal 0. Because it's in a radical, it can't be negative. It would have to be greater than 0. It would have to be greater than 0. Any questions on that? Okay, so what's the domain in this problem right here? X would have to be what? Instead of greater than or equal to, it's greater than 0, greater than 5. Look at these two. What's the difference between these two? These two. They're almost exactly alike, aren't they? This one's greater than or equal to 0 because it's in the numerator. Okay? And this one is greater than 0 because it's in a denominator. Okay? Any questions on that? Okay? What's the domain here? 5, comma, infinity. Okay? 5, comma, infinity. Yes?
If it was the other way around, if 5 minus x and negative
All right.
x,
All right.
still the same?
What if it's 1 over the square root? This is a new problem. Y equals 5 minus x. That doesn't look right. 5 minus x. Okay? Now, what's the requirement? What's in the radical, which is what? 5 minus x. Do you see that? Must be greater than 0, which means what? Negative x must be greater than how much? Now here we're going to negative 5 on both sides. And therefore x is what? Less than what? 5. Okay, less than 5. In other words, here x must be a number that's smaller than 5. For example, what? Give me a number. 4, 3, 2, 1. And listed in interval notation from what to what? Negative infinity. Anything up to 5. Now try that up here and see. Look at the equation. What if you said x is 4? Would that be okay to have 4 here? What if you said 3? Would that be okay? What if you said 2, 1? Right? Anything less than 5. Now it can't be 5, can it? What if it's 5? Then you'd have 5 minus 5, which would give you a 0 for a denominator. See, so it can't be 5, because that would make a denominator 0. What if it's 6? Can't be 6, because you'd have 5 minus 6 is a negative 1. You'd have a negative 1 in a radical. So it can't be 5, and it can't be 6, 7, 8, 9, or 10, or anything larger than 5. It has to be less than 5. Okay? Any questions on that? All right? Now, the fourth category, I've saved category 4, and category 4 is the easiest one of all. Category 4 says, what if there are no denominators and no radicals? Then what are the restrictions? No restrictions. There are no restrictions. Now, if there are no restrictions, what's allowed? Everything. Okay? If there are no restrictions, then everything's allowed. So what's the answer automatically? Let me get my pink chalk. It'll be all reals, all right? All real numbers. And that would be from what to what? From negative infinity to positive infinity. Okay? Any questions on that? Okay? All right, now, I've covered the first, let me say 2 more things. On page 4 you have an example of each category. of each of these four categories on page 4. And then at the bottom of page 4, I want you to look at the bottom of page 4. What about number 1, 2, 3, 4? Those are all the same category. Can you tell me what they are? 1, 2, 3, and 4. They're all the same category. They're all category 1. Because they're all denominator problems. Okay? They're all denominators. Denominator only. Now look at 5, 6, 7, and 8. 5, 6, 7, and 8. You're going to have all of those involve radicals. Okay? All of those involve radicals. And what about 9, 10, 11, and 12? All of those involve radicals and denominators. And what about 13, 14, 15, and 16? No restrictions. There are no radicals, no denominators in any of 13, 14, 15, and 16. So the answer is automatically all real numbers. Which would you like to have a lot of on the test?
13 and 14.
All right, that's it. All right, now, with that, then that finishes that portion of the video and that portion of this class. And then next time we'll continue with an explanation of how to identify the functions, domain, and range from the graph. That's what I'd like to do next time. All right?